listen, do you think you could explain to me, like, why I'm dressed like this and what those big words in the sky were all about and, like, where we are in time?
Your home, Bricksburg, is one of many realms in the universe. There's also this one, Pirates Cove, Knights Club, Vikings Landing, Clown Town, a bunch of others we don't need to mention.
Mm-hmm.
Blah, blah, blah. Proper name, place name, backstory stuff. Is the special. Put the piece of resistance onto the Craggle and disarm it forever.
Great. I think I got it, but just in case, tell me the whole thing again. I wasn't listening.
All right, folks, so let's cover the second midterm. I'm not just going to go through these straight up answers. I'm actually going to go through kind of a review, get through these topics again, and refresh our minds of all the different things that we've covered in the second half of the course. All right, so let's take a look at this first question over here. What we're dealing with is one of those mass spectra, ESI, for a large molecule, a protein, and we're asked to do a protein deconvolution. So in other words, we're trying to calculate the mass of that big compound over there from all of the different charge states that we see. So hopefully you remember this. We've seen this before. So this is an example of a protein where we have different charges, and depending what that charge state is, you'll see it at different regions on the mass spectrum. So here's a nice simple example. If we know the mass of our compound, let's say it's 12,000. If it shows up singly charged, then you'll have one signal at, well, roughly 12,000, 12,001 if it's a proton. But if you have 2 protons or 3 or 4, it'll show up at half or divide by 3, divide by 4. So we'd be able to calculate and predict the m over z values of all of these different components just by adding the number of protons and then dividing by the charge state. Now, what the question on the test is actually asking, well, we don't know the mass. We have the mass spectrum. We're trying to figure out what these masses are. That seems like a problem because how do you know what the charge state is? But that's not a problem because we can figure that out as long as we know the 2 charge states next to each other are just differing by 1. And we won't go through the derivation here. We've done that before, but we have this equation and it's provided to us on the test. Okay, so we take a closer look at our masses and let's apply that equation. So the first thing we want to figure out is which mass is 1, which mass is 2 according to the equation. And it says here that m over z1 is the higher mass. So let's just pick these 2 over here. Now I'm going to calculate the mass difference between these 2. So subtract 1 from the other. We get a mass of about 74. Let's retain all those digits. Now, why did I pick these 2? I didn't need to. In fact, I'm going to do the calculation with all of them. So here's the mass difference for each and every one of these charge states that we see. Now, the next part of the equation, it's m over z2 minus 1. So I'm taking the smaller mass and I'm subtracting the mass of a hydrogen. I would like to put in the exact mass of hydrogen, not just 1.007825. So that's the numbers that we see over here. Then we just do the division between the 2, and we got to go back and think about which charge state this applies to. So referring to the equation again, this is the charge of the heavier of the 2 masses. So I'll slide these over here. The other thing we should think about is that these are charges. They're integers. It has to be plus 1, 2, or 3. It's not 14.998. So I'm going to round these all off. Exactly 15, exactly 16, 17, 18. And of course, the one at the top, it's got to be a charge 19 as well. So the last part of the problem, all I'm going to do is subtract the exact mass of hydrogen, multiply by 19, and I will get the mass of my compound. I could do that with every single one of them. So when you calculate those masses, they all turn out to be roughly 25,000. And actually, I might as well use all of these numbers. So I'm just going to take the average, report a standard deviation, get all fancy with that. Now, for this test, given the time frame, I wasn't expecting everybody to calculate this with more than 1. It would be more than fine to calculate with just the 1 and take it into account simple significant figures. All right, so that answers the first part. The second part of this question is now to say, what is the mass of one of the compounds near A? So let's just take a closer look at the answers that we have so far. We know the charge states up to this point. Which one are we missing? Well, I mean, it's going to be plus 14, right? Well, you can see that it's just going up to the next one on the scale. So I know that that compound, that m over z A has a charge state of 14. I also know the mass. I mean, you just calculated from part A. So I'm just going to take that mass, add the 14 protons, and then divide by a charge of 14. So that's the answer. And of course, depending which exact answer you reported for part A, you might get a slightly different number than what I have here. Now, part C of the problem asks us to focus on that blue signal, the lower mass, which I've labeled B. And it gives us a little bit of the origin of that mass. It says that it's a difference of 1 glycosylation unit, so a hexose sugar with a mass of about 162. This corresponds to the mass of the uncharged compound. So when I'm thinking about the mass difference between A and B in that spectrum right there, I have to consider what charge we're dealing with. So we have a spacing of 162, but a charge state of plus 14. So all I got to do is divide that by 14 and then subtract it from the mass of A. And again, depending which masses you've used exactly, you might get a slightly different number. You could do this a different way. You could go to the original mass, subtract the 162, then divide by 14. It would work out to be the same thing. Now, part D of this is kind of a different question altogether. So no longer dealing with calculation, but we're going to probe this glycosylation site. Specifically, the question is, where is it? So we're asked to describe a bottom-up experiment, and we've talked about this before as well. A bottom-up experiment is one that first takes a big protein and digests it with an enzyme like trypsin. Almost always it's trypsin, and it breaks it down into smaller pieces. So we could imagine our compound over here. Well, the only difference is that there's a glycosylation unit somewheres in there, but the trypsin won't really care about that. It'll still break this down into peptides and will generate a bunch of different fragments. The next step of this is to do an LC-MS experiment. So we talked about data-dependent scans before. Basically, we take our entire sample, throw it into a chromatogram, and then we're going to generate a whole bunch of MS spectra, specifically tandem MS spectra, for each and every peptide that we can try to get an identification on. So peeking at the data over here, we would do the same thing for, well, I've just shown 2, but we would have a lot of tandem MS spectra generated for as many of these compounds as we can, hopefully all of them. Now, what do we do with that data? Well, this is a matter of using a computer to interpret the information, and what we have to our advantage is that the spectra we've collected, we can compare them to a database. That database would represent the possible sequences of what we can deal with. This is just one protein. So that database is just generated from the specific antibody and its known amino acid sequence. And then we just start go ahead and matching, and we put some scores onto these things to try to find which peptide corresponds to the unknown that we have. Of course, this won't be too complicated because really there aren't that many peptides being formed. It's going to be the one whose mass represents the theoretical mass from a trypsin digestion. So this is our database. It's just one single protein. There's its amino acid sequence. I mean, you wouldn't know what the sequence was for the test, but it's something that could have been looked up. So we would have digested this sort of theoretically, generated all the peptides, generated the BY ion sequence from those peptides, and done the matching from there. Now, what about the question of that glycosylation unit? So how does that affect the information? Well, it affects it quite a bit because the database to this date doesn't incorporate that modification. And if I don't have that in the database, then the data is not going to make sense when I start trying to interpret it in the computer. So I need to kind of polish that database. This strategy will work when I don't have a glycan unit on any of these peptides, so that one's identified, no problem. But for the other one, the one that has that glycan unit on it, what I'm going to need to do is massage the database, somehow change the masses. And that's easy to do. You just say, well, we know the masses, let's just place it wherever it might go. Of course, we know that certain amino acids can incorporate sugars and others can't, but that didn't really matter right here. So we modify our database to incorporate that glycosylation unit, and then we use that to identify our sample. All right, so we're going to switch gears here on to question 2, completely different application. We're dealing with EI fragmentation, specifically for this compound diethyl ether, and we're trying to interpret the fragmentation pattern. So in this question, you're going to be reminded it's more like organic chemistry, where we're asked to draw a reaction scheme for one of the products. And you know, to talk about like whether it's homolytic cleavage or things like that. Hey, we've done that before as well. So we described that we can get different forms of fragmentation, whether the electrons are moving as a pair or whether they're coming one to either side. And that's a matter of generating radicals, generating neutral species and things of that sort. So we can apply that as an example to, wow, a remarkably similar compound to what was on the test. And you can see an example of a homolytic cleavage right here, bond breakage, and the products that would form from there. So we didn't have to worry about whether it was an alpha or sigma or beta cleavage, but that's another thing that we talked about. So you can see the products that we formed. The key thing here is that if you start with one charge, you have to finish with one charge. If you start with one unpaired electron, then one of these products is going to have an unpaired electron in it as well. So let's apply this specifically to our compound here. So this would be a hypothetical structure for our diethyl ether. I just subtracted one of the electrons from the lone pair on the oxygen. Now, since the question says it's up to you which one you want to pick, I'm completely randomly going with this. I'm just going to say what happens when I do a homolytic cleavage at this particular bond right here. And as it turns out, we're going to generate this product here. There's the charge state, and then of course we have to have something on the other side. It's just a methyl radical. But notice the charge of the methyl, there's no charge on it, and therefore we're not going to observe that mass at 15, even though you can see the mass of 15 in the spectrum. Not for this particular case. But the other part of this product does have a mass, 59, and that seems to explain what that prominent peak would be right there. Just to try another one, see what happens, let's try moving the electrons together, and it looks like we're going to move the charge to the other side. This time, well, we're not detecting that side because it doesn't have a charge, and to add up the masses, 29. So there we go, we've seen 29 in the spectrum as well. Now, part B of the problem is asking us to draw the predicted fragmentation of the mass at m/z31. Now, this compound's a little bit harder to predict, but it is saying that it's basically a secondary fragmentation of an original fragment, the one at m/z59. So we already drew that from the previous question. So just to see what we're talking about, it's like we go from 59 down to 31, therefore there has to be a loss of 28. So here's the fragment for m/z59. And all I know right now is that we've lost 28 and produced 31. Now, where does 28 come from? Well, let's just start taking some guesses. I mean, C plus O, that adds up to 28, but so does C2H4. So I'm just looking at the structure and saying, well, C2H4, it sits right there, whereas CO sits in the middle. Okay, not quite. I mean, this isn't C2H4, it would be C2H5. There'd be a methyl on the end of that. So how can that be solved? Well, this is where we talk about rearrangements. So you don't necessarily break one single bond. Sometimes you can create these new compounds. And the key with a rearrangement is that we have a neutral loss. So HCl would disappear, just like we might lose C2H4. So I'm kind of going with that right here. I'm not really worried about how that proton moved, but let's just sort of say that it did. Now it leaves me, if I break the bond, I can form C2H4. So that seems to be a stable, neutral molecule that would lose. And then the resulting other side of it, not a charge state on that, but the other compound might look like this. So that seems like a relatively stable compound as well, m/z31. And in fact, it seems to explain why we have such a prominent signal in our mass spectrum. 31 is the biggest peak. All right, so that does it for the applications. Now we're going on to the instrumentation. And rather than just ask the questions as, I don't know, draw me a picture of a time of flight, explain how it works, that kind of stuff, I phrase these types of questions in the form of the context of resolution. So we really talked about resolution a lot in this class. We said that some mass analyzers are better than others at maintaining high resolution. We also explained the problems associated with mass analyzers and why they limit resolution as well. So in this question, you're asked to discuss the limitations of resolution and ways to fix it, with the only caveat being you can't repeat the same answer twice. Because I know what you'd probably be thinking. You'd say, yeah, the Boltzmann distribution. Boltzmann distribution, kinetic energy, seems to apply to all of these cases. You can only apply that to one. So which one are you going to apply it to? It's kind of up to you. It just sort of fixes your next answer. So I'm going to think, let's go with the magnetic sector. Why? Because the magnetic sector separates on momentum, mv. And v is part of the kinetic energy, 1/2 mv squared. So in other words, our ions have natural distributions in their velocity. Therefore, they're going to have differences in momentum, even though they're the same mass. So that's a problem when it comes to a magnetic sector. So I'll put the Boltzmann distribution over there. And I also immediately think of a nice little solution that we can do. It's not immediately just sort of use the same instrument, but I can modify that instrument. I can turn the magnetic sector into a better form of magnetic sector, electrostatic sector. So the combination of these two sectors working together, electrostatic followed by magnetic, is a way of compensating for that energy distribution that we would normally see from a Boltzmann. So we'll just write that down over here. Add an electric sector without going into too much detail about how that works. Okay, for the time of flight. So we're not allowed to talk about Boltzmann distribution anymore. So what are we going to say? Well, we talked about the time of flight, our ions going through this drift tube, basically a race to the finish line. One discussion with that was about the fact that all of these ions have to start at the same time and at the same place. So you see over here, like that green ion, the big one, seems to have a head start over the white one, so that's really not a fair race. So what we need to do somehow is make sure that all ions are starting at the exact same point, that they don't experience this head start. We talked about MALDI, for example, as a way where all of the ions are fixed onto a metal target. In fact, they're not even ions until the laser fires them, and then they get ionized, and simultaneously the race begins from there. So that's just one strategy we could talk about. Another way, which wouldn't involve MALDI, is to kind of eliminate that process altogether. The extra head start that they have, well, let's change the angle. So now they're in an orthogonal injection mode. So yeah, that ion beam, maybe some ions are moving faster than others, but they're not moving faster in the direction that matters. So an orthogonal time of flight is another way of handling that head start distribution of ions. So we come down to the last one, FTICR, which we always say has the highest form of resolution, and that's because of the way that the ions are detected. So we're using an image current, and you're seeing here the theoretical current, which is sort of up and down in relation to how big those ions are. But in actual fact, those currents decay. And the reason they decay is because they lose energy. There's collisions with residual gas within the ICR cell. So how do we solve that? Well, basically it's coming down to vacuum. So if we can remove all of the ions, then we're going to have a longer opportunity to measure the decay. You could just say, for example, measure the ions longer. So that would be a simple answer to describe in this as well. Okay, continuing now with mass analyzers. Now we're going to talk about a quadrupole ion trap, and specifically how we use the quadrupole ion trap to do an SRM type scan, selective reaction monitoring, which we normally talked about, what we did talk about in the context of a triple quad. So now let's just say, how can we do an SRM scan with a quadrupole ion trap? So the first part says, let's draw a picture. There you go. This is the picture taken straight out of the notes. Yours can be as pretty or as whatever you want it to be. Make sure that you got a ring electrode, the end caps, the ions in the middle between there. You can put the detector in the source region on either side. It also says to talk about the AQ stability diagram. So just make sure which one is on the X and Y axis. Goes into the negative, which isn't even that important. The stable region is defined as the space in the inside. The unstable region is on the outside of that little diagram. Okay, so when we put these two things together, what we're seeing here is that our ions are normally held in a DC equals 0, so RF only mass scan line, which means that the end caps are being replaced with no voltage. We just keep our RF supplied to the ring. But there is another voltage applied. So if you remember this here, there's something called a secular frequency. You imagine that these ions are kind of dancing around in here. They all have their characteristic frequency. And if I tune into that frequency, you can supply an RF or AC frequency, which is going to be added to the end caps because that's what you're seeing right here. And that's going to excite a specific ion. In fact, I could apply as many of these extra frequencies, secular frequencies, as I want to, in the form of some type of a pulse. And that could be done to excite every single ion except for the one that I want. Now, once I do that, it's just a matter of fragmenting that ion. So I have one ion left inside the ion trap, add a collision gas, helium, and then proceed for the fragmentation. Okay, so I think I've summarized all those steps right there. It's a matter of trapping the ions, isolating them, fragmenting them, and then detecting the fragments. And it's really just a combination of supplying that RF voltage to the ring to keep the ions that we want in there, and then the supplemental RF voltage to the end caps to kick out the ones that you want. All right, we're almost done here. We're talking about different forms of ionization. And once again, it's not just about, draw me a picture of what these sources are. Instead, I'm going to be asking this in the context of quantitative analysis. So with quantitative analysis, all we really care about, but one of the things we care about a lot is that everything's going to be staying the same. You want to trust the signal, it needs to be stable. So if you're using these different types of ionization sources, we want to think about the parameters that might influence, that make things ionize more or less. So just a reminder of what these things are then. Chemical ionization, well, it's kind of like EI. So you imagine the EI source over here. We have an electron beam that's being accelerated at a specific voltage, kind of like 70 electron volts. And here's where the change comes in. our sample is going to be introduced into the space, but on top of it, we have this background gas. So I'm showing methane, but it doesn't need to be methane. And the idea now is that those electrons, they're more likely to hit into the methane than into the compound itself. So in doing that, we're going to induce some type of chemical reaction. We're not directly looking at the methane reacting with our analyte. Rather, it's the methane with another methane. We can make a species that might look like this. So this really strong acid, CH5+, which will then be involved in a proton transfer with our analyte. So what type of parameters would matter? I mean, you could talk about the type of gas, you could talk about the concentration of the gas, certainly that electron voltage that we're applying to it. There's any number of things that you could do that would alter the efficiency of this process. So moving on to electrospray ionization. Basically, the idea is that you have our metal needle, we spray a liquid, it's in our analyte is already in solution, and we get a proton transfer already in the solvent system. So we have an acid in that solvent, and there's simply a proton transfer. And from there, the process is just a matter of getting rid of the solvent, evaporating it, but there's those Coulombic expansions and fission events that's going to ultimately produce the gas phase ion. So what matters here? I mean, the type of solvent, the type of acid, the pH, the strength of the acid, especially when we think about how that solvent needs to evaporate. So you talk about the solvent composition, how much organic solvent we have in it, the temperature of the source, the voltage that we apply, the distance to the needle. There's a lot of things that can go into that. Basically, you could think of any process involved with the electrospray and say, yeah, that thing is important, and mention that. So MALDI is the last one here. We're dealing with a matrix, and these compounds are designed to absorb our UV laser light. So you can see they all have chromophores in them. They also have a functional group to them that basically donates a proton. So what we do from here is we embed our sample within that matrix. There's going to be a controlled ratio between the matrix and the analyte, and then we start firing our laser onto it, and then we get this explosive type event that's going to ionize from there. So the type of matrix, the laser power, the way that you deposit the samples. We talked about like how these deposition methods will influence the depth, the thickness of these crystals and things like that. So there we go. That pretty much does it for part 2. We're talking about instrumentation and a few applications. Right now, the class, we're talking about all kinds of different applications and many new forms of instrumentations, all of which are going to be relevant for the final exam, remembering that there are lots of choices in those questions. But I do like the types of problems that kind of incorporate the new stuff that you guys are talking about with some of the classic things that I've been presenting over here. So just think of ways that kind of combine things, compare things, ask the questions. I've been saying this all along. Think of the kinds of questions that you might be asked. These are the questions that I like to ask. There's many different forms, and I'm going to guarantee you that every single time I ask a final exam question, it's something I've never asked before. It's a brand new form of question. So good luck with that. And we'll see you around next time.